Troubleshooting MSTP networks can be a challenging task. Here at KMC, we have been working with these networks for as long as they have been around. We understand the challenges and how difficult it can be to isolate issues on your network, especially when there are multiple issues present on one network. In this video, we're going to show you how to properly locate issues on your network using a multimeter. We will show you the most common issues, the readings that these issues will show, and the root cause of the problem. And while it can seem much simpler to try to diagnose your network from a workstation with software, using a multimeter and bifurcating or splitting the physical network cable will help to resolve this issue much faster. We're going to start with issues that are impacting the entire trunk. Start by putting your multimeter into ohms to measure resistance. Check the resistance between the shield and the ground. If it is greater than 3 ohms, the shield is not grounded at all, or is not connected to a good ground. We are reading nearly 0 ohms, which indicates normal behavior. If we read less than 3 ohms, when you remove the ground, you are grounded in more than one place. Find the extra ground and eliminate it. The lesson here, be sure to only ground once on your network. Let's switch our meter now to measure DC voltage. Start by checking the DC volts between the B+ and A-. If your measurement is below 200 millivolts, the B+ and A- are shorted together somewhere. And now we need to bifurcate, or split the network, and start as close to the middle of the network as possible and split the network in half. Now, use your meter again and measure the readings on both sides to narrow down the issue. This will tell us which side of the network the issue is on. Again, let's bifurcate that side of the network and narrow again. Repeat this process until you find 1 or 2 controllers that could be the problem. In the same process, if your DC volts between B+ and A- show above 500 millivolts, one side is not connected at all. Staying in DC volts, check the B+ side to ground pin on the controller. If it reads a steady 5 volts or 12 volt signal, the power or signal for a sensor is shorted to B+ or A-. The same problem will show by also checking A- side to the ground and getting a reading steady of 5 volts. To fix, repeat the process of bifurcation to find the suspected controller and sensor. A 3 volt to 5 volt signal can also be introduced in the network because of a net sensor wire that is miswired or crushed. Next, check DC volts between the B+ and the ground. If the measure is less than 700 millivolts, there is a short or a strand touching B+ to the shield, or a wire is stretched or crushed and is causing this. The same issue can also be seen by checking DC volts from A- to the ground and seeing less than 700 millivolts. In either case, we must bifurcate to find the issue. Now, let's change our meter to read AC voltage. Check the A- to the ground. If it is greater than 2 volts AC, some source of voltage is shorted to the COM or controller is misphased, and usually you will see 24 volts AC or so. Also, you can check the AC volts between B+ and the ground, and if it is also greater than 2 volts AC, the same issue is present. Bifurcate to find that issue. Now we're going to simulate an issue here on our own network at KMC Controls to show how useful bifurcation of the network can be for the speed and diagnostics of the issue. We're going to check our voltage between A and B and see how it's changed. And now we see we have 0.01, 0.02, and before we had 0.2. We're going to go down the line here and take our network wires apart and check to see which side of the network the problem is on at this controller down the hallway here. That shows a low reading. Switch wires, so we've got the other half of the network on now, and that shows high. So our problem is down the wire with a low reading. So he goes on down that way, so we know our problem's down that way. That's where our low voltage is at. And we check our voltage, and our voltage is low. And then we check this one, and we have high voltage. So now we know this side of the network is where our problem's at, because it had the low voltage. And we just follow the wire that's got the low voltage all the way through the network. We're going to bifurcate up here at another spot. This is our next spot that we have located. It's an easy spot to get to. So we'll climb up in the ceiling and see what we have up here. Now, as I've climbed up here, the first thing I've noticed is that the end of line is on this controller, and it's not supposed to be on. This is in the middle of the network, so that end of line should not be on. But before I change that, I'm going to check the voltage on the network, and we have 0.12. So that tells us it's too low. So I'm just going to go ahead and flip that end of line to off, and we're going to recheck the voltage, and voila, we got 0.22. That's a good thing. Okay, now we're back where we started, and we want to double check the voltage, see if it's back to normal. So we've set our meter to DC voltage, and we're going to check it, and boom, 0.2 millivolts. That's what we want. It is also important to note that the issues in the field may not be caused by the terminations themselves, but instead it is the wire itself being stretched out, crushed, cut, or just plain bad. We always recommend that you bifurcate the network. For more videos on troubleshooting networks and building automation systems, check out our other videos. And to learn more about any of the solutions from the building geniuses at KMC, visit us on the web at kmccontrols.com.